Ok. ¿Sí, ¿me escuchan bien? Sí, bien, ok. Bueno, buenas tardes. Bienvenidos todos al cuarto día ahora del panorama. Pues todas las charlas han sido muy interesantes y me gusta ver que también hay mucha interacción entre todos. Pues hoy nos va a presentar Horvath, okay, y voy a dar un resumen de su, ¿cómo se dice? De su trayectoria. Okay, en español, espero que esté bien. Okay. Bueno, él originalmente hizo su licenciatura en el Instituto de Meteorología en Budapest, en Hungría. Después obtuvo su maestría y doctorado en Ciencias Atmosféricas en la Universidad de Arizona, en Tucson, el Instituto de Física Atmosféricas, de donde vienen los cientistas atmosféricas mejores del mundo. Dentistas, perdón, científicos, perdón, eso fue español. Bueno, pero se entiende que son los mejores del mundo. Um, y hizo una gran serie de postdoc y bueno, en JPL, en JPL, como lo tradujeron, Laboratorio de Propulsión a Chorro, okay, en Pasadena. Y también pasó un tiempo en UCLA, en Los Ángeles. Y pues ahí conoció a Simona. Okay. Actualmente él trabaja en el Instituto Meteorológico de la Universidad de Hamburgo, en Alemania, ya lleva un tiempo allá, y él se especializa en propiedades macro y micro de nubes y en particular usando imágenes de satélite. Okay. Uno de sus desarrollos, no sé, originales es un algoritmo de recuperación de vientos por los movimientos que se observan con los satélites, y eso es usando el instrumento multi-angle Imaging Spectrometer, MISR, okay, pues siempre parte de ese proyecto. Y últimamente, y eso va a ser interesante para mucha gente de aquí, se ha concentrado en usar imágenes, el uso de imágenes geoestacionarios de muy alta resolución, que ya están llegando a muy alta resolución de minutos y casi cientos de metros, para investigar la evolución espaciotemporal de, bueno, ellos tradujeron como columnas, no sé si así se dice, columnas volcánicas, como yo diría pluma, ¿no? Okay. Y pues también otra cosa interesante, en las islas que está por ahí por Baja California, ha investigado ondas gravitacionales que se genera por la misma isla. Y también, pues, ¿cómo se dice? Dinámica de vórtices generadas por esas mismas islas. Entonces, pues, vamos a darle el bienvenido a Arcos. Okay. Okay. Bueno, no sé si se hace hablado. Okay.
Oh, yeah. So is it on? Okay. So yes. So thank you, Dave, for the, I believe, nice introduction, even though I didn't understand a word of it. So I welcome everybody to my talk. First, this is my first time in Mexico City. But Mexico City is, for my generation, has a reputation because in 1986 there was the World Soccer Cup here, and Hungary lost 6-0 to the Soviet Union, and this was a catastrophe. And my generation still thinks it's a catastrophe. And the excuse was that because we are lowland people, Hungary is in the Pannonian Carpathian Basin, the elevation was so high that the footballers couldn't really compete. And I always thought it was a fake excuse, but now that I'm here, we walked through campus and I really lost my breath. So I think there's something to it. Okay, so I'd like to thank the organizers. I'm having a wonderful time here. They're showing me around in Mexico City, and it's really an honor to present some of my work here. So the I'll try to talk about two things. I hope I have time for it. So the first topic, which was the laser. Oh yeah. So the first topic, which is the main part of the talk, concerns volcanic plumes, the satellite remote sensing of volcanic plumes. And my background is the satellite remote sensing of meteorological clouds, so water clouds. But in the past 6 years, I've been part of a German research consortium called VOLImpact. This is our logo. And it means the impact, volcanic impact. So the proposal literally is titled to preparing for the next big eruption. And the goal was, it includes both modelers and satellite remote sensing people to prepare both satellite remote sensing tools and advance the modeling of atmospheric plumes. And we were very lucky because in the first 3 years of the project, we had 3 pretty big eruptions which went up to the stratosphere. The one I show here as an example is the La Soufriera eruption in the Caribbean in 2021. But beforehand, we had Raikoka in 2019. And of course, we had the gigantic Hanga eruption in 2022. So all this gave us a lot of opportunities to develop our tools and advance or try to model all these eruptions. And the second topic, if I have time for it, is basically my pet project, my hobby horse. It's again the satellite remote sensing of this KÁRMÁN vortex reeds. One example here is the island of Guadalupe. You can see a nice vortex reed in the lee of Guadalupe. And this is a very good island to study this phenomenon because it very frequently produces vortex reeds and it has an interesting shape. Okay. So these are the 2 topics that I'll try to cover. Okay, so as a motivation. So we started the project in April 2019, and literally a couple of months later, we had the Raikoka eruption. Raikoka is an island in the Kuril Island chain. So I started to collect satellite data, and this is an animation loop from the Himawari geostationary satellite. You see every 10 minutes, you see an image. It's an image loop, and you can see the plume. It was a long eruption, 20 hours. And there were like 10 or 12 individual phases of the eruption. So that satellite sits a little bit west of Raikoka. Then I started to collect other satellite data. This is on the right. This is the GOES. It's an American geostationary satellite. It's basically the same imager, exactly the same imager, but GOES sits more east of the island. And as a result, the island is really at the edge of the image. So this black area here is space. So now this gives you a very, very different perspective of the plume, of the eruption. You get a much more sense of the depth of the vertical development of the plume because you're looking at it from a very oblique angle. You're looking really at the side of the plume, not from the top. So the motivation was for me trying to get something out of this very oblique view. Okay, so in the next slide, I'm showing the same thing, but what I do here is that on the top right, it will be the Himawari data, but it's remapped into this equirectangular projection. Usually the satellite, these geostationary satellite data are not the raw data is used, but you remap it into some more common web projections. The left side is the same, but for the GOES, again, in the same equirectangular projection. And the bottom is the GOES again, but in the native view, but I rotated the image. So basically when the plume erupts, it erupts along the y-axis. So these 2 panels show the same data in different web projections. And what you see is that, again, it presents a very different view of the same event. So the main message here is that the world looks differently from angles, or from different web projections. So usually you use this data, or if you go to the NASA WorldView website, this is the data that you get. And if I can stop the animation with 1 point. Okay. So the native image, this is how the satellites use the plume. The triangle is the volcano. You very nicely get an idea of the vertically evolving plume. If you use it in the regular web projection, it gets very, very distorted, the image. So it's much better to use data that's on the edge of the satellite disk in the raw data format. All right. So now a little bit of a background of the actual satellite data that we're going to use. So the main tool is this advanced baseline imager on the GOES satellite. There are two satellites now, three, but two operational ones. These are geostationary satellites, so they always hover over the same point. And the GOES West looks mostly in the Pacific, but you also see the US. The GOES East is centered more on the Americas. So it produces three different types of imagery or data streams. You get a so-called full disk image every 10 minutes. The entire disk is imaged. In the smaller area, so-called conus area, you get 5-minute imagery in both cases. So Guadalupe, for instance, also included in both of the conus imagery. And in an even smaller, so-called mesoscale areas, these are 1,000 by 1,000 kilometer boxes, you get 1-minute imagery. And these guys are moved around the mesoscale domains. They usually follow hurricanes or tornado genesis or deep convection, so weather. But they also move them around following volcanic eruptions. So they moved it to the Hanga eruption, the GOES 17 domain, and they also moved it to the Ulsuflera in 2021. So these are the imagery that we use. And what you get, it has 16 channels. So this instrument has 16 channels. You get this is an example of full disk image. And what we're going to use mostly is the red band imagery. It has the highest resolution of 500 meters. But we also use the brightest temperature, the infrared brightest temperature data, which is 2 kilometer resolution. And you get the temperature out of it. So we use it for the developing the getting the physical temperature of the cloud. I'll keep pushing this thing. All right. So this is the imagery that we have. We're going to use. Now we can derive many things from the satellite data, but the most important thing that I'm going to focus on is simply the height of plume height. So plume height is important for several reasons. One of them is because where you eject the material, of course, it really determines how the plume will spread, because the wind profile. So the wind changes with height. So of course, it's important to know where you eject the material. It's also important because there's a big distinction between tropospheric and stratospheric ejection. If you put it into the stratosphere, it stays into the atmosphere for a long time, and it can have a climate effect. So height is important for that reason. For modelers, it's also important because they need to initialize their models with the injected material. And what they do is that they determine or estimate the injected material from the height of the plume. And the classic way to do it is using the so-called Sparks masking curves. These are two scientists who developed this parameterization. So what you see here is the y-axis is plume height, and the x-axis is this mass eruption rate. Notice that it's a logarithmic scale. And the dots here, these are individual eruptions where the volcanologists went out in the field, or they had sort of in situ or ground-based remote sensing data, so they can have a fairly good estimate of both of these parameters. And the important note here is that it doesn't include satellite data. So these are all quote-unquote in situ, where the volcanologists have some faith in their retrievals. So what you see is there's a correlation between plume height and mass eruption rate. Bigger plumes usually are associated with more mass ejection, but there's a lot of scatter. But nevertheless, they published a couple of simple fits to this parallel fits to this field data. And basically, the rule of thumb is that the mass eruption rate scales as the fourth power of plume height. And the important thing here is that a small error in height can give you a large error in the mass eruption rate. Now, this is still a classic way of initializing a model. A more modern way is basically the same, but instead of using this empirical formula, what you do is you can use a 1D plume rise model. For instance, F-plume is a new one that is very popular, and you embed it into your GCM or weather forecast model. And this plume model uses the forecasted weather, most importantly, the wind and the temperature profiles, so accounts for the changing weather. And the most important thing is wind, because it can tilt the plume, and basically a height, the same height can refer to different mass eruption rates depending on the wind. If there's no wind, you get the plume goes higher for the same mass eruption rate. So we use both in our simulations. The point is that you really need height, plume height as an input data. Okay, so how do we retrieve plume height from satellite data? The classic method is the so-called temperature method. And it's basically based on looking at an infrared channel imagery and taking the minimum temperature of the plume that's assumed to be the best one to characterize the maximum plume height. And you use a temperature profile. So I'm showing two cases. On the left, it's Lassofair. It's a tropical profile. So you use a temperature profile, in this case from era 5, for instance, and you find the temperature, the height that corresponds to your measured plume temperature. The drawback of this method, or the problematic issue of this method, one is that your satellite brightness temperature might not actually refer to the physical plume temperature. For thin plumes, you can overestimate the temperature because you see the surface a little bit, so your height will be underestimated. The other one is that you can have multiple solutions. So I'm showing it here. If you have a plume temperature 260 Kelvin, you have one solution, it's around 7 parameters. Now, if you have a lower plume temperature, 210, then you have two solutions. You have a tropospheric solution and you have a stratospheric solution. And it's difficult to decide which one to use. This problem, these multiple solutions, can be more exaggerated for other areas of the world. So on the right side, you see a case for Raikoka, which is a mid-latitude case. So the temperature profile here has a huge 10-kilometer isothermal layer, which means that if your plume is around this temperature 220, in this case, you basically can have a plume height anywhere between 10 to 25 kilometers. So this is a fundamental issue with the temperature method. Okay. Now, the next slide shows the summary figure from a fairly recent validation of all these temperature methods for tropospheric or volcanic plumes. So what we show here is on the y-axis is the brightness temperature-based plume height versus the LiDAR heights from the Calliope satellite. So these are all cases when we had an overpass from a polar orbiter satellite with the LiDAR. It's an active method. So this is considered more of the true. So this is the true height. We believe in it much more. And what you see is there's a good correlation, but there's a big bias in the brightest temperature-based heights. You tend to underestimate the real height up to 3-4 kilometers for top high plumes. And again, remember that mass eruption rate scales as a fourth power of height. So this can cause a big error in the assumed mass ejected into the atmosphere in the model. Okay. So the alternative is the so-called geometric method. And the geometric, I'm showing two of them. The classic way is when you have satellite, when you have a view of the same object from two different directions, then you can retrieve from the two views the geometric height of the plume. It's basically how your eye perceives depth. So you have two views, and then in this case, you get the depth of the object from the two views. Now we have a whole bunch of geostationary satellites around the globe. Here I'm showing the two US GOES satellites, and this is the Japanese Himawari and the recently launched European Meteosat third generation. They basically all have this very similar capabilities now in terms of image quality and timing or frequency. So when they have an overlap area, you can do the stereo retrieval. The Hunger eruption was viewed by both Himawari and GOES West. And for instance, Guadeloupe is also in the overlap area of the two GOES satellites. Now, how does the stereo retrieval work? How does it work? So if you have I'm demonstrating it on a meteorological cloud. So you have a cloud, and then you have one view, one satellite. In the image, this cloud will be projected to this point. If you have a second view, then you're going to project the image of the cloud to this point. So there will be a difference between the two image locations. It's called parallax, and from this parallax, you can get the cloud top height. This works if the images are very well synchronized. So they almost at the same time look at the same real estate. Now, if you have a slightly asynchronized imagery, so there's a couple of minutes or seconds between the views, then you have to tackle the issue of cloud motion or motion. So if the two satellites look at the cloud different times, in between the views, the plume can move with the wind. So you have now two unknowns, the wind and the height. So you need at least one more image. So two disparity or parallax measurements. And from these, you can pull out both the wind and the height. Now, the advantage of the geometric methods is that it's a very simple sort of high school geometry method. It doesn't depend on any ancillary profiles. It's not subject to the same uncertainties as the brightness temperature method. It's simple geometry. Okay, so this is the classic method, and it's not new. So stereo methods have been used for a long time, but within this project, we developed a very flexible code which can combine almost all the existing geostationary satellites and polar orbiting satellites and pull out the wind or plume motion and height. Now, the one particular technique that we newly developed for this project works in a very specific case, and I call it a side view technique. So if you look at a full disk image, geostationary image, you have the sub-satellite point, which is right in the center of the image. This is a location where the satellite is right above you. And you have, so the view angle is zero, it's in nadir. And as you move towards the edge of the disk, you're going to look at the Earth from more and more oblique angles. This yellow line here just demonstrates the threshold of 75-degree view angles. And this is sort of a threshold angle above which people really don't use the geostationary data. So products are produced, but in this area, which I call the limb, this area is basically thrown away. So what we try to do is we try to exploit exactly this limb view for plumes. Because a lot of interesting volcanic regions sit on the edge of this image. So La Soufrière sits here, the Kuril Islands and Kamchatka, they sit there, and Ulavun, another big eruption in 2019, was there. Okay, so what do we do? I usually demonstrate this with the TV tower of Hamburg. This is the iconic TV tower in Hamburg, but we are here in Mexico City, so I replaced it with, is it the Torre Latinoamericano? Okay, so if you have this is our first order model of a plume, an eruption plume, just a big tower. So you, an observer, you're sitting here, it's the star. If you know your distance to the base of the plume or the column, then what you can do is you simply measure the angular extent from the base to the top. And then you just, high school math, you just multiply these two together and you get the height. So this is the essence of the technique. But what we're going to do, we do it from the geostationary satellite distance. And why it works is usually I told you that for stereo, for geometric metric techniques, you need 2 or 3 images at least. In this case, you can pull out the height from one image because you get one piece of information for free. And this is that we know the base location. We know that when you have a plume, at the beginning of the plume, so the technique only works right at the beginning of the eruption. When the plume moves away, it doesn't work. But that's what you need for inertializing model. So we know the vent location. And that extra piece of information basically helps us or allows us to take out the plume height from one image. Okay. So it's a little bit of technical information, but we use the best channel is the red band visible channel. It has a 500 meter pixel resolution. So you have the satellite here, 36,000 kilometers from Earth, and the pixel size, the field of view is 14 microrad in this case for this satellite. So when you look at the equator, it corresponds to, at this distance, 500 meter pixel resolution. Now, as the satellite scans, when it scans the edge or the course to the limb of the Earth, the same 14 microrads corresponds to almost a factor of 10 larger footprint. And this is one of the reasons why people don't like the edge of these geostationary images, because if you look at surface features or clouds, horizontally extensive clouds, then you really have a very blurry picture. But if you look at a column or mountains or eruption columns, which are located or aligned along the local vertical, then you basically recreate the same view geometry as in the equator. So looking at a vertical column at the edge of the disk is basically the same as looking at the surface at the equator. So for in the vertical direction, your pixel resolution is almost the same as at the equator. All right, so now I'm just demonstrating it here on a couple of, how do we do it in practice? So this is one example, La Soufrière from GO17. This is one particular eruption, and you see basically the side view of the rising plume. So we know the location of the vent of the volcano, and basically you can draw these height lines, height scale. We can put the height scale on the image. So 1 pixel corresponds to 500-600 meters height. And that's how you basically determine the plume height. In this case, you can by eyeball it that this is the top of the plume, and you get a height of something like 17 kilometers. Now, this is the same plume from the other GO satellite, which views it much more from the overhead direction. And the things you notice is that the plume sort of shrinks. So its vertical extent is much smaller in the image because you shorten the view. And also this vertical scale gets pushed down, which means that you lose sensitivity. So 1 pixel now corresponds to a much larger vertical height. So the technique works best when you really look at high view angles. But in my personal experience, if you look at the plume at 50, 60 degrees at least, you can get decent height retrievals. And this is just the intermediate view angle. The point here is that as the view angle decreases, you keep losing sensitivity of this technique. Now, we can validate it on mountain peaks. I'm doing it. Okay. So Kamchatka has a bunch of volcanic peaks. So here I'm choosing 3 different cases, 3 different mountains with different heights. So we know the location of the base, and the yellow dot is just the height of the peak. And simply you measure the distance between the base location and the height, and it increases for the 3 mountains, and you can pull out these heights for these mountains. And we know the height for the true height of these mountains. I did this exercise for 50 peaks, and this is the scatter plot. I'm plotting the estimated peak height from versus the true peak height. So you get a pretty good retrieval. It's my guess, my estimate is that around 500 meter kind of accuracy. So it's competitive with or better than the brightness temperature method. Okay, so the next question is where you can apply this technique. I'm showing the 3 satellites that I showed already, Himawari, then the 2 GOES, and this for each of them I show which the actual total field of view, and this band here is the band of the limb, the edge of the plume. So what you see is for Himawari, you really see the active Alaskan volcano region at high view angles. For GOES, you see Kamchatka and the Kuril Islands, Papua New Guinea, also a bunch of South American volcanoes, Vasufera, and even probably El Popo is probably viewed at a good enough angle that you can make some height estimates for that. And GOES 16 mostly views the Icelandic region, which really caused havoc a couple of years ago when the transatlantic air traffic was shut down. So I'm waiting for a next big Icelandic eruption so I can test the technique on these volcanoes. Now this is, but we have more than 3 satellites. We have a whole bunch of geostationary satellites. The point of this figure is that basically every single major volcanic region is viewed by at least one of these satellites at a high view angle. Okay, now there's a saying that there's nothing new under the sun, and it's true. I discovered that this technique has been used by the planetary science community already. This is an example from the New Horizons mission, which flew past Pluto, but on the way it also imaged the Io, which is a volcanically active moon of Jupiter. It turns out that we actually they pretty well mapped the location of volcanoes on Io. So as the satellite flew by, it was lucky enough that there was an eruption. It happened that the volcano was right at the edge of the image. And this is exactly what they did, like what I just explained, that they just measured the distance between the known volcano location and the plume. And in this case, they can estimate that on Io, you get plume heights up to 300-400 kilometers because it's a low gravity environment. So there's nothing new in the world. All right, so I hope you get the basic idea of how we measure plume height from this technique. So I'm just going to show you a couple of examples. So let's start with the famous Hanga eruption. This is the view of Hanga from the GOES satellite in January 2022. And this, the first 2 hours of the Hanga eruption, it became the largest ever measured plume. It went way up to the mesosphere. So in the next image, I'm just taking one slide or one snapshot out of this sequence when the plume was the highest. This is the 4:30 UTC image. And I said Hanga can be imaged both by GOES and Himawari. So these are the same plume from two different directions. And you can do the stereo method that I mentioned. Now, usually we do the stereo method automatically. So we have a software that tries to identify the same image feature in the two images. But this is such an extreme case that our automated stereo matching software failed. It couldn't find the same image feature in the two images. So we had to go back to square one. The human eye and brain is still the best pattern recognition instrument. So I manually had to basically find the same features on these two images. So here is one point here, and that corresponds to this point in the other image. And from this, you could pull out the height. And I did it for 30 different points over the plume. And these are color-coded here. And the main point here is that you get a plume height up to 56 kilometers. And this was the Pinatubo eruption. The previous big one only went up to 40 kilometers. So that was I think we were the first to have a peer-reviewed publication on this record-breaking eruption. But we can also do this. We could validate our technique. We could use just the side view method too. This plume was also imaged by a third geostationary satellite, the Korean satellite, and it was further east. So it looked at this plume at a 60-degree angle. So it's good enough for our side view method. And it basically confirmed our stereo retrievals. Here is the known location of the volcano. And simply measuring the number of pixels to the top, it was 95 pixels. So at this view geometry, it corresponds to 57 kilometers. So we could validate the top height retrieval even from the side view method. But we can do more. So in the later phases of the eruption, we could apply our automated stereo method, and we can get the height and the motion of the plume out of the GOES and Himawari retrievals. This is a sequence of this plume height and plume motion retrievals. The color is a wind vectors or plume motion vectors, and the color is just the height of the plume. And you can use this data to basically study plume dynamics, because it was such a extraordinary plume. All right. So this is one slide, one frame out of this sequence, which really demonstrates why the brightest temperature method doesn't work. So here are a retrieval at one particular time. What we do here on the right plot is that I'm plotting the geometric retrieved height as a function of the brightness temperature of the given pixel. So we think this is the true height, and this is what the brightest temperature method would use. The curve is the temperature profile. Now, if the brightest temperature method would work, then all these points should be around that curve, which would mean that the temperature, from the temperature, you can retrieve the true accurate height. What you see is there's a huge scatter. So let's just take one group of points here. Here, the true height of the cloud is something close to the tropopause, but the temperature is so high. These are thin plumes, so you probably see the surface. So if you use the temperature to get their height from the temperature profile, you will get a 5-kilometer height. So it's a very good demonstration of the power of geometric techniques. Okay, so I think I need to speed up. What you can also do is that we had some plumes which were imaged from the ground-based webcams. So this is an example in Kamchatka, the Shiveluch volcano, and we had an image from the local webcam. So this is the same plume from 36 kilometers and 36,000 kilometers. And if you have, you can do this technique from a webcam, if you have a calibrated webcam. And we basically got the same height as the local volcanologist. Now, I just learned that El Popo is also viewed. There are webcams. So basically, the same technique could be used, validating or comparing the satellite, these retrievals for El Popo. This is an image from Dave. So it's from a smartphone. But I know that there are no webcams, which are much better for this purpose. All right. So I'm just going to show one more example before I move to the next topic. So the technique uses the visible channel, which is only available during daytime, but you can do it at nighttime too, from the brightness temperature images, but at a little lower resolution. So this is a eruption, Passo Freire, and you see the side view, the top view, and the same in the visible channel, and then the infrared channel. And the point I want to make here is so the plume goes up. When the plume is relatively small, then you don't see the plume in the infrared image because there's so much water in the atmosphere that it basically dominates the signal. But if the plume is high, it goes above something like 12 kilometers, then the plume, at least the top of it, also appears in the IR image. So the technique can be used for large plumes even at nighttime. Okay. And that's just, let me just see. Okay, I'm going to talk about it's the same deal, but this was the biggest plume of the Passo Freire eruptions. So just an example. All right. So what I want to do here is, so this is a technique, and I'm going to show you one example how it can be used to get a better forecast. Through the example of Raikoka. So the left image shows all the eruption phases that we identify from the satellite, more than a dozen different plumes, and we can estimate the height of the plume, so these individual eruption phases. From this, we create an eruption sequence using the plume height and plugging it into either the Mastin model or the weather-aware F-plume model. And this mass eruption rate data set is then inserted into the model. And we plug in this eruption sequence into the model and let it go, and basically forecast the spread of the plume in 2 days. The plume first moves out to the east, the North Pacific, and then there's a cyclone there, and it sucks in the material and turns it back. So and this is also the summary slide of the first part of the talk. What we do here is then plotting the total erupted ash amount as a function of time. Now, we have, from the satellite, we can also estimate the mass of the ash. And this is this black curve here. There's a big uncertainty on it, but nevertheless, this is our best guess for observations of the mass atmospheric ash amount as a function of time. Now, if we use the green curve is our very first model simulation, which simply used just a fixed height, 12 kilometers, and a 20-hour continuous eruption with some eruption rate. So the very beginning, when people want to get a quick forecast, they just do use some realistic numbers, and usually constant eruption. What we see is it really overestimates basically in the first 12 hours the ash in the atmosphere. And the other other color curves are when we use the satellite-derived eruption sequence, so we can have a good idea of the height and in the length of the eruption. And if you plug it in, then you get a much better agreement with what we think our best estimate from observations of the ash amount in the atmosphere. Okay, so this is the summary of the first actually most of the talk. Basically, the take-home message, which is not a surprise, if you have a more accurate description from these new instruments of the eruption sequence, you get a better forecast. Okay, so I'm talking like, how much time do I have more? 5 minutes. Okay, so I don't think I can go through in 5 minutes, but so maybe 10. Can I get 10? Okay. So the next topic is very different. It's a classic fluid dynamics problem, but we use again the GOES instrument to measure the winds or this problem in the atmosphere. So we have this classic case of the KÁRMÁN vortex thread. When you have it's a flow channel, and you have a cylinder in the flow, and then the flow comes on the left of the image. Then at certain Reynolds numbers, it basically starts to shed these counter-rotating vortices. This is the von Kármán vortex thread. And it's called a KÁRMÁN vortex thread because Kármán, who is also Hungarian, so I have to study this problem. Kármán was the one who first gave a very simple analytical explanation of this of the geometric structure of this street. Okay, so in the laboratory, that's the first image was just a numerical simulation. In the laboratory, you get these patterns. Here's a cylinder, and then you get these 2 rows of counter-rotating vortices. And why it's called, as I said, a Kármán vortex thread, because Kármán was the first one who did a very simple linear stability analysis and showed that this is the staggered arrangement is the only stable one, and he even derived some specific numbers for the aspect ratio of the vortex thread, so how wide, what the distance between the 2 rows, and also the distance between the same rotating vortices. So now this phenomenon occurs on different scales, and there's an atmospheric analog, which is happening behind islands. And here is the case that we analyzed. This is Guadeloupe, and then it's a whole day of satellite imagery every 5 minutes, and you can start to see this vortex thread vortex shedding from in the lee of the island. Now we switch to daytime. The previous was nighttime IR imagery. Now we have the daytime imagery, and this vortices move down and then lose strength. So from this imagery, we can actually retrieve the wind vectors, and that's what I'm showing here. Oops. So the same input imagery that you showed allows me to, oops, I'm going the wrong direction. Get the wind vectors, wind retrievers for this case. So it's all derived from this satellite sequence. You can see the wind vectors maybe. This is basically it can be only done now with this new very high spatial and temporal resolution geostationary imagery, and we can now explain the formation of these cloud patterns from the retrieved wind field. So this example I'm showing here, I'm using the previously retrieved wind field, and I'm starting advecting a checkerboard pattern with this satellite retrieved wind field, and I colored a couple of different boxes, which will show this will deform in very different ways by this wind field. And basically, you can now very nicely describe how you get these cloud patterns that you see in the real satellite imagery. You can also derive vorticity in different ways from it, and clearly see the shedding of the cyclonic and cyclonic vorticity. And now we can do analytical studies comparing the atmospheric case with the lab case. So the Kármán vortex field is a very well-studied subject. There are thousands of papers, literally thousands of papers on it. But now we can compare all the accumulated knowledge about the laboratory case with the case in the atmosphere. Okay, so now I'm gonna skip all the other slides. We can do many things, but the bottom line is, just for the sake of time, is that with the new, there was really an explosion of satellite technology in the last couple of decades, and with this really high spatial and temporal resolution data, we can now study these unsteady mesoscale flows and the dynamics and relate back to the hundreds of years of history of laboratory vortex studies, because it's not clear that the atmospheric case is really a complete analog of the laboratory case. There are many differences between these two cases, but there are also similarities. And I mean, I'm happy to, if somebody's interested in it, I can show all the slides that I skipped through, how we can study, for instance, the decay of vorticity as a function of downstream distance and compare it with the laboratory findings. All right, so I stop here. And thank you for your attention. Okay, so now I just saw, well, yeah. Dave told me that I should shut up after 15 minutes. All right. Okay, so one thing that we see is that this vortex field is asymmetric. The cyclonic and anticyclonic vortices decay differently. And that's what I'm showing here. We track these vortices from the satellite imagery, and I'm plotting the vorticity as a function of distance from the island for the anticyclonic blue and cyclonic red. And what you see, and this is a robust result, is that the anticyclonic vorticity decays faster than the cyclonic vorticity. And you can also see it in the imagery around Guadalupe, that the cyclonic vortices are identifiable for a much longer time than the anticyclonic ones. Now, the question is, what causes this asymmetry? And in the lab, when you usually have a cylinder, a very axis-symmetric object, or what is it called, obstacle, the only way to get an asymmetric vortex shedding is to rotation, so introducing the Coriolis force. And this is what you see here. This is the top view of laboratory vortex field. This is the cylinder, and you see that the cyclonic vortices are much more compact than the anticyclonic ones. They tend to bake up. It's the same image from the side. So here is the big cylinder. The flow comes from the left, and these are the cyclonic tubes, and these are the anticyclonic ones. And what you see is that rotation with Coriolis force introduces an instability into these vortex tubes, and that's why these anticyclonic vortices break up quicker. Now, Guadalupe is not an axis symmetry. It's not a cylinder. So a cylinder is not a good model for the shape of Guadalupe. It's more like an aircraft wing. It's a flat plate. And it's been studied in the lab for a long time that wings also produce an asymmetric vortex field. So this is a laboratory image of a wing, aircraft wing, or airfoil, which is a better model of Guadalupe. So in a wing, you can define a leading edge and a trailing edge, and you see the vortex fields. And what they found is that the trailing edge vortices are basically more stable than the leading edge vortices. And this also comes out when you do numerical simulations. So in case of Guadalupe, this could also be the case. You can define a leading edge and a trailing edge, and the trailing edge vortices are the cyclonic ones. So what we did is that we did a warp simulation where you can just play with the orientation of the island. So this is the actual orientation of Guadeloupe, and you can just turn it around in your warp simulation, and then you can run the model. And this is a summary figure. The point is that the vortex rate really depends on the orientation of the island, and the finding is that this is, in the case of Guadeloupe, the main cause of the asymmetry. It's not Coriolis force, but that it's really like an aircraft wing. So in this case, we could really explain by numerical simulation what we found out from the satellite imagery. So yeah, that's it. I think that's enough. Okay.
Bueno, ¿algunas preguntas? ¿Preguntas?
No question.
No tengan miedo. Okay. Arturo?
Thank you very much, Jacques. I was wondering what kind of Reynolds numbers would this correspond to?
Say it again.
To what kind of Reynolds? What number?
Reynolds number.
What would you put in that
right, so
simulation?
In the lab, I think vortex shedding starts at a Reynolds number of 50. That's when this instability comes in. And the images I showed you, it were like 150 and 300 Reynolds numbers. In the lab, you can get vortex shedding at really high, thousands of Reynolds numbers. It gets more turbulent, but it's a large range. Now, in the atmosphere, I'm not an expert in it, but it's difficult to relate the laboratory Reynolds numbers to in the atmosphere. You have this molecular viscosity and everything. So that's still an issue of how to make a correspondence between the laboratory Reynolds numbers and in the atmospheric case. 150, 300 Reynolds numbers you don't get if you use the regular kinematic viscosity of air. You don't get vortex shedding in the atmosphere. You get at a much higher numbers. So there are these tricks of using, I think, molecular or some effective viscosity, eddy viscosity, to really make the laboratory case comparable with the atmospheric case.
Right. And just one last comment. In your previous material that you showed, I was wondering if there have been efforts in Hamburg to use the wind velocity as a in assimilation cycles, regional models. Have you tried that already?
The wind velocity of
and the velocity that you get from clouds.
I mean, yes. So the cloud motion winds, it's a regular product from pretty much every satellite operator, NOAA, EUMETSAT, JAXA, etc. So these are assimilated into ECMWF, for instance, and I think even the US models. So they track clouds in all different kinds of channels. So you get tens of thousands of wind retrievers from satellites, and these are assimilated into operational models.
Even for regional models?
Regional models, that I'm not super familiar with those, but the big global models, definitely, they all use. And in fact, it's usually now most of the data is from wind, comes from satellites. So the radio sound is so sparse that you use the satellite data.
Okay, thanks.
¿No? Muchas gracias, Acos. Muy interesante la plática.
Oh, okay.
Okay. No?
No? Okay.
There's some,
yeah, that's fine.
There's translation.
Yeah.
Otherwise I can... Okay. Bueno, el punto es que hay muchas cosas que uno empieza a pensar viendo tu plática, es muy interesante, pero Una de ellas, me pregunto, muy probablemente ya lo han hecho, es identificar la altura de los ciclones tropicales, de los huracanes, porque eso siempre es una variable muy importante para poder pronosticar adecuadamente su evolución, tanto en trayectoria como intensidad. Y sin embargo, pues hay las ambigüedades que tú mencionabas. Entonces, me pregunto si eso se ha utilizado para ello.
So can you maybe, because it wasn't super clear.
The top of the hurricane heights, which is what density and things like that.
Right. Right. Yeah. Sorry. Yes. Okay. So I'm working with colleagues from NASA Goddard and Jim Carr, who has his own aerospace company. So yes, they have papers when they use the stereo retrievals of hurricanes and claim that you can get a better description of the dynamics because you really can track accurately both the height and the wind around the eye, and also basically get a better forecast of the path of the hurricane. So the answer is yes, it's been used by my colleagues for hurricanes. There are many applications that I didn't show, which my colleagues use. I focused on the use of these methods just for volcanoes, but for meteorological clouds, severe weather, yeah, they have been used. There are papers on that I can send you if you're interested.
Aaron?
Yes. By observing the Kármán morphology, can you guess, for example, velocity of the atmosphere? Because I assume that if you have different velocities, the shape of the Kármán changes. So you can guess other variables, like, for example, wind velocity that was going through.
Yeah. So the vortex shedding only starts at a certain wind speed. So the Reynolds number or the Froude number, there are all these bunch of numbers, non-dimensional numbers that you can derive. So usually they start at 10, 50 meters per second wind. The size of the vortices are primarily determined by the physical scale of the obstacle. So for Madeira, which is a much wider island, you get much bigger vortices than, for instance, for Guadeloupe. Where the wind comes in is the vortex shedding frequency. So how frequently the vortices are shed. And that's really controlled here by the upwind wind field. So yes, you can guess, there's a correlation just looking at the wind, how frequently the vortices come one after the other. You can probably guess the upwind, the island wind, upstream wind.
Graciela? Creo, ¿no?
Yeah.
Graciela, ¿no?
Yeah. Thank you very much for your presentation. I know that the Hungatonga explosion introduced a lot of water vapor really high up, and you showed mostly the visible to estimate the height. But has your group analyzed the spread of the water vapor and the actual, not just the ash, pretty much? And okay. That's okay. It. I was going to ask something about this, the vortex shedding as well. That in terms of the analog with the laboratory work, because clearly here you see the vortex shedding when you have stratocumulus clouds, and there may be a little bit of an inversion or a step in the density between the subcloud and the cloud base, right? And so what is the height of the island and what's the cloud base height?
Might have so let's start with the second question. If I had a backup slide. So about the vortex shedding, the laboratory vortices are really thin and then very tall vortices. The atmospheric vortices are so-called pancake vortices. So they are very short, not very tall, but 30 kilometer in the diameter. So that's one difference. But yes, so these vortices only occur under certain stability conditions. So this is what I show here. The temperature profile has to be has to follow what I show on the left. So there's a capping inversion on it, and you can derive this so-called Freud number, and it has to have a specific value of 0.4 at least for the vortices to develop. The point is that you need quasi two-dimensional flow. The flow has to go around the island if there's not above it. If the conditions, atmospheric conditions are such that most of the air can go above the island, then you don't get vortex shedding. So that's a difference, for instance, from the laboratory flow, and also the actual vorticity production mechanism is much different from the laboratory flow. But in our case, we found very good, even numerical agreements, for instance, in the decay of vorticity with published values from the lab. So there are big differences, but a lot of the laboratory results can be even quantitatively hold up in the atmosphere. So the first question is hunger. So yeah, it's a lot of people studied. It was an underwater eruption, and it put something like 10%, increased the stratospheric water content by 10%. And yes, NASA groups use the OMS instrument, for instance. Limb viewing instruments are in the UV range, are the ones which are really used for the spreading of the plume. So plume, I was a couple of months ago at the hunger workshop in Paris where they showed basically the plume is being tracked now for more than 2 years, and you can still see the atmospheric water vapor now spread over the entire planet. But the disappointing result for hunger, for climate modelers, is that its radioactive effect is basically zero. So they were hoping, because it was a much bigger eruption than Pinatubo, and Pinatubo introduced a 0.5 degree decrease in the surface temperature. They were hoping at the very beginning that hunger will be the first eruption which will cause a warming, because of the water vapor dominates the output, not the ash. And there were very early studies in Nature which got published that it will be a positive effect, but now after 2 years, basically it's going to be almost zero. A net effect is zero. So in a climate point of view, it's not an interesting eruption. But it was such a gigantic shock to the atmosphere, and this is a thing that I'm studying with Dave. It introduced gigantic land waves, sound waves that circled the planet several times, and we are studying its propagation through North America using, among others, GPS stations in Mexico and pressure data. You can clearly see the propagation of the sound waves through the North America.
Natalia. I was wondering, like, what kind of effects does this vortex of ash have in comparison to normal distribution of ash? Like it can go farther than the normal distribution of ash events, or?
You mean the vortex heat, are you talking about, or
yes, the transport by the vortex.
So the vortex is it is a cloud. So it's a volcanic island, but it's really, it has nothing to do with ash. But you're right that these vortices, they happened also in the ocean. So the oceanographers actually are much more advanced in studying these vortices because they mix nutrients and they mix phytoplankton, and so there are lots of studies in the oceanography literature about these vortices because fish go to certain areas where there's more nutrient mixing. So it's much better, much more studied in the oceanography than in atmosphere. In atmosphere, they don't really have any practical effect. It's more of a curiosity or blue cloud research. There's one particular case where I saw papers in vortex sheet. Madeira Island also produces vortex sheets, and the airport is at the south of the Madeira, Funchal, and the planes basically have to take off or land into the vortex street. And there were a couple of cases where now Madeira is a very slowly moving, produces very slowly moving vortices because it's a big island. But there were a couple of small biplanes, Cessna, so individual people who got in trouble because there was vortex shedding. And for the small planes, there was even a crash somewhere because it introduces turbulence, or it actually introduces a wind shadow. So the wind is really decreased after the island, and then the plane just plunged because it flew into, the relative speed to the air became slow and then just plunged. So that's the only practical case I've seen of vortices.
Jimena.
Sí, hola, felicidades por la plática, estuvo... sorry.
Yes.
Muchas felicidades por la plática, estuvo buenísima. En la primera parte del material donde hablaban de que falló el reconocimiento de patrones y que se tuvo que hacer como de forma, pues como manual, ¿por qué, a qué se debe como esa falla de patrones? ¿A qué cree que lo atribuye? Esa falla.
Okay, so the question was that why we couldn't identify, I had to use manual vortex, manual stereo matching for this case. Well, I mean, you can try yourself. I mean, if you, there's a point here. Can you easily identify where it is? So the pattern matching techniques, what they do is they select a little chunk of the image, a little patch, and they try to find its analog in the other image. And it works relatively well when there's not much variation in the height. But when there's very large variation in the height, and you view it from two different angles, you simply can't recognize the same feature. So you can think of yourself, you try to retrieve your face or your height of your head. If you have an imager that looks at your face, but the other imager looks at the back of your head, you can't match the two, right? I mean, your face will not have a nose, you don't have an analog on your head. So there's no matching pattern. But if you're a human, you can create a mental 3D model of these things. And I spent hours and hours on it. But after a while, when you close the windows and everything, you get vertigo. But basically, you start to recognize patterns that, okay, here is a big column. And if I look it from the other side, that would be the analog. And after a while, you can really do it. So it's simply because of the large, very large variation in the height and the very, from two different views, you just don't see the same features. So what you notice is you only get retrievals on this side of the cloud because that part was not imaged by the other satellite. So this part here, it would be at that side of this dome, but it's blocked by the other side of the dome. So obscuration, but mentally you can clearly identify that this is the east side of the dome, which should be somewhere there.
Okay, Irma.
I will speak in Spanish.
Okay.
¿Es posible con su modelo determinar qué ciudades serán afectadas en su calidad del aire?
Cities? So which cities?
Like, for example,
mhm.
how much we transported relative.
Yes. So we did simulations for all these eruptions, Raikoka and Lasufrera in Hanga. And Lasufrera was the most interesting case because it produced a lot of ash. And we also, our institute has a site on Barbados, which is 150 kilometers downwind. We have radars and lidars. So that was, we have a whole run. And basically that was the whole goal of this project was to develop tools where you can do, really initialize the model with good quality data. And then you have an accurate prediction of ash spread and also ash amount, how it falls out. So that's the goal.
Because to find particles is very important for these sources.
Right. So I work with people from the Karlsruhe Institute of Technology, and these are the chemists and aerosol modelers, and they are the ones who basically define what kind of particle distribution you put into the model. So that's their expertise. But there's some uncertainty along those lines. My goal was just to give the height, and then how they distribute and what they distribute within that height range. It's the modeler's, let's say, responsibility.
But it is possible to calculate it.
I mean, so you can have EC2 measurements, and then it can give you constraints on the particle size. So what we did, we had many runs and different initialized setups, and then we compared with the satellite data, which one gives you the best agreement, for instance, with the observed spread of the plume, because you can simply visually track the plumes if it's dark brown, colorish. So these are the things that one can do. And then if you have ensemble runs, and then you can pick the one model setup that is the closest to the observed reality.
Thank you.
Yo creo que ya, ¿no? Ok, bueno, yo creo que ya vamos a cerrar. Entonces, pues le damos otra demostración. Bueno, Xochitl, no sé dónde estás, pero iba a hablar con Ecos. Y si otra persona quiere hablar con él, podemos hacer como una reunión y mañana va a estar aquí todo el día. Bueno, hasta el fin de semana. Entonces, si alguien quiere hablar con él. Nada más, yo mandé un correo.